Welcome to this new webinar. As you have seen from the title, so we are going to talk about the new shell elements that we implemented in OpenSees and in STKO. Now, there are many things that I would like to talk about these elements, so I'm thinking about dividing this webinar into two parts. I will explain something today, the basics, how they work in the elastic analysis, what's the difference between this new thick shell element or shear deformable shell elements with respect to the existing shell elements in OpenSees. And then all the aspects related to the nonlinear behavior, I will do it in the next webinar, so it will be easier for you to follow. Just before we start, you know that the ASDShellQ4 was in OpenSees already from 1 year, probably even more. And the triangular counterpart has been added recently, and it's in the OpenSees official website, but you still have to wait for the OpenSees developers to compile the latest versions of OpenSees. So probably within the next few weeks, a new version of OpenSees will come out, or probably Professor Tarke will compile a preview of the next version. Okay, but in the meantime, I will start to explain you something about these new elements. Okay, so let me share my screen and then move to the other PC. Okay, so just before we start, let me show you what I will share. I close a couple of things here. So I have so many windows open. Okay, so what you will find into the files that we will share, there are basically 3 sets of examples. I will start with the fixed plate, which is a basic example in which I compare the different shell elements, the different formulations, so the thick shell elements or shear deformable shell elements, with the thin shell elements, which are the ones that were already in OpenSees, and I will compare them to the solution given by solid elements, so you can understand when you can use one or the other. Then I will do the same for the in-plane bending part, so the behavior that these elements have in terms of being able to bend internally in the plane of the element. And then I will spend some word about the co-rotational part, which is the ability to represent large rotations. Okay. And then all the things about the material nonlinearity, I will explain them in a next webinar. So just before we start, I want to show you where you can get the documentation. So as you know, the ASDShellQ4 is already available in the official OpenSees documentation. So if you go in the OpenSees documentation, you go in element command and you search for ASDShellQ4, you will find it here. The SHellT3 is not yet, it's in the source code, so you can visualize it in a preview, but it's not yet in the official documentation, okay? But I will use it to explain it a little bit of things. If you are interested in the reference that we used to develop these elements, they are all here, okay? So I explain what is the formulation that we use for the membrane part, for the drilling DOF, for the out-of-plane part, for the linear co-rotational kinematics, and you have all the reference down here, and all the reference can be downloadable, okay? So you can go through the articles if you're interested in the theory. And the same thing for the triangular one, okay? So let's first start with explaining what is a thick shell element. So I prepared just a simple image here. So as you may know, a shell formulation is a simplification of the reality, of course. Is a simplification that you can use when you have a structural member that has one dimension which is smaller than the others. Okay, then how smaller, we will see it later on. But one of the dimension is smaller. In this case, is the thickness. If this is true, you can use the shell assumption. Now, what happens when you bend an object, a 3-dimensional object like this? You will experience shear deformation. So the displacement in the cross section in the in-plane deformation will be like something like this, will be a cubic deformation that generates the well-known parabolic shear, transverse shear deformation. When we use a shell element, of course, we are not able to represent this cubic deformation, and we are fine with it. With the shell elements, if the thickness is small, we can assume that the cross-section remains straight. So basically, the first assumption that we do, let me go here. I need this one. Sorry. Okay. Go back to the image. And the notation. Okay, so the first assumption that we do is that, okay, we cannot get this curve deformation, but we are fine with the assumption of flat cross sections. Okay, so a cross section planes is flat before deformation and remains flat. Okay, so this assumption is fine. Now, there is another assumption that we typically do with shell element, is that this cross section is flat, but also remains normal to the midplane. And the normal to the midplane at this point is this one, okay? Now, assuming that the cross-sections remains normal to the midplane, consists in assuming that there is no shear deformation at all, okay? So this is fine when the shell is very, very thin. And I will give you some number later on with the examples. When we cannot assume that the shear deformation are not negligible, okay, we need to use a shear-deformable formulation, which is the reason why we introduced these new elements in OpenSees, where basically we assume that the cross sections that remains flat does not necessarily remain normal to the plane. So as you can see here, I have the normal to the plane, but my cross section can have a different rotation. Okay, so the total rotation minus the different rotation will give me the shear deformation. Okay. And this one will be used to create a shear-deformable model. Now, what I'm going to explain is what happens if you neglect it and when you can use previous formulation or not. Okay, so let's stop. Let me remove all the drawings. Okay. And let's go to the example. Okay, so the first example that I will show you is here in the fixed plate. Here I prepared 3 files, okay? One is called fixed plate 1 to 10, where 1 to 10 is the ratio of the thickness to the size, to the characteristic size of the plate, okay? So 1 to 10 is moderately thick, 1 to 12 is thinner, and 1 to 40 is even more thinner, okay? So we will see how the different formulations behave and how they compare with the solution given from a solid element, okay? And in each one of them, what you can find. So I will show you the first one. Let's start with the 1 to 10, okay? So 1 to 10 is, if you go through the literature, is the typical limit between a thick shell and thin shell, but it's actually a very strong limit. In this case, you will see that the thin shell does not compare exactly well with the solid solution. Okay, so when you will open this file, I will just briefly explain you what you will find. You will find 5 geometries. In the middle, there is a solid element, which is split in 2, just to have the middle plane, okay, at the same level of the other shells. The size of each one of them is 10 units, and the thickness here is 1 unit, okay? So in this example, you have a ratio of 1 to 10. Then on the left-hand side, you have a thick quadrilateral element and a thick triangular element, where I will use the thick shell element in the ASDShellQ4 and the ASDShellT3. So these two are thick formulation, shear-deformable or Reissner-Mindlin, okay? On the other side, you can see instead the existing formulation, which are the DKGT, which is here, and the DKGQ. Okay, so triangular and quadrilateral counterpart for the Kirchhoff law or thin shell elements. Okay. Now, as I said, I will not explain now these settings because they play a role in the material nonlinearity, and I will talk about them in the next webinar. So now I want to focus on the difference between the ASD shells, the thick shell elements, and the thin ones, okay? So here it is the geometry. If you look at the mesh, it's not very fine. I used a 0.4 unit of mesh size. So you have a quadrilateral here, triangular here, hexahedral in the middle, and then once again, triangular and quadrilateral. Then we go through the boundary conditions. We have boundary conditions for the shells, which is a complete fix on all the sides, okay? And then the boundary condition for the solid that best match the condition that we made for the shell. So I put a constraint in the X and Y degrees of freedom through the faces, which is basically avoiding the rotation, okay? And then I fix the Z displacement only in the middle so that we allow the shell, the solid element to expand or shrink in the out of plane direction because the shell has this assumption. You know, the shell does not have an out of plane stress, which means the thickness can, it doesn't actually stretch, but internally can have an out of plane deformation that is calculated automatically in order to have an out of plane zero stress, okay? So this one is the typical constraint that you can put on a solid to have the same solution. And then in terms of loading condition, a simple pressure, okay? So at 10 units of distributed force here, and in the mid plane of the solid, okay? I didn't put it on top just because I want to reduce the numerical differences between putting an offset on a load, okay? So I selected the internal face of the solid. And then few steps. So I have a recorder. I just want to see the displacement, boundary conditions, a simple load pattern. Here I'm not focused on doing strange thing. I just want to show you how they compare to the solid solution, if they diverge from it, or what are the limits in which you can use the thin element or the thick elements. Okay, so if you run this analysis, you can run it with a simple sequential OpenSees. You don't need a parallel version. It's very small. You go to the post processor, and the output will be called exactly as the input file, okay? So we open the fixed plate 1 to 10. Okay, so I will switch off the mesh just for a bit, but as you can see, you have quad, triangular, solid, triangular, and quad. Now let me look at it from the top, and let's see what is the solution that we have here in the solid element. Okay, so I isolate it, and I see that the maximum displacement is 17 here to the -4, okay? 1.7 to the -4. So this is the maximum displacement I get from the solid element, and we take it as a reference solution, okay? Now, if I look at the thin shell elements, as I said, 1 to 10 is a typical, let's say a limit to use the thin shell element, but you will see that also with this limit that is often used in literature, the thin shell elements start to be a little bit too stiff. So if I isolate them, you will see that it is not, it's slightly less, okay? So 1.4, 1.5. If you go instead to the shear deformable one, you will see basically the same result. So I isolate this one, and I have 117, exactly as the solid element, okay? So the point is that 1 to 10 is a very strong limit. If the thickness is even higher than that, okay, you cannot rely on a thin shell element. Now, to see if the thin shell element converges, you can try smaller thicknesses, like we can go to the 1 to 12, 1 to 20. Okay, this is the same file. I just scaled the solid thickness, and I changed, of course, the thickness of the shell element. Okay, so now it's not 1 unit, it's 0.5. Okay, so if you can run this other one. And you can go and have have a look at what happens with a ratio of 1 to 12, 1 to 20, okay? Now the solutions are much closer to each other. So let's start with the reference solution here. We have 1 to 1. Let's go to the, well, let me go on top view, it's easier for selection. Let's go to this one, the thin shell element. We are close enough. It's not exactly the same, but it's much closer than it was before. And if we go to the thick shell element, either the quad or the triangular element, we are still at the same value, okay? So the thick shell element is able to capture the response even in the thin shell limit, and then I will talk about this, okay? As you can see, the thinner the shell, the better is the prediction of the thin element. But the thin element cannot be used in the thick limit, okay? So let's do a last trial with the 1/40. This one is really thin, so we expect the thin shell element to have a good behavior. Okay, so in this case, I scaled once again this one, and I changed the thickness to 0.25. Okay, you can run this one. And let's go to the post-processor and open the 1/40. Now let's go to the reference solution. If you isolate it, you will see that the maximum response is 938. Let's look at the thin elements. Is 939, so it's very close. Okay, and the same thing happens here. Okay. So in this case, we are on the same page. So basically, all of them can give you the same result. So what is the point here? When you use a thin formulation, you can only use it when the thickness is really small compared to the to one of the characteristic size of the plate. Okay. So typically in the literature, you will see 1 to 10, 1 to 20. 1 to 10 is a very strong limit. It's better if you are a little bit below that. But the key point is that if you have a thick plate and you use a discrete Kirchhoff element, the dk, GT, or GQ, the response will be stiffer. So you are going to underestimate the displacement that your slab will have, okay? Why this happens is because of the extra constraints. So if I go back to the image, as I said, the thick element, so the shear deformable, allows for this deformation here, which is shear deformation, while the thin elements imposes another constraint. So not only the faces remains plane, but it is forced to remain normal to the midplane. So since you have an extra constraint, the solution will be stiffer, okay? So the point is, why do we need, I mean, we can always use the thick shell element at this point. And I can say yes. So basically, I always use thick elements because they perform well both in the thick case and also in the thin limit, okay? So you may ask, why do we have these formulations in OpenSees, but also in other softwares? It's basically for historical reasons. So until a few decades ago, I mean, if you use a basic displacement-based formulation, it's easy to formulate these elements, but it's a mess to formulate them. Because if you use a standard displacement-based formulation, these elements will show a problem which is called transverse shear lock. So if you are interested, you can go on some references. If you go on here, you will see that I talk a little bit about the plate bending part. So the plate bending part is treated using the MITC formulation. Here you have a reference, which is used to avoid the well-known transverse shear locking problem. Now, I will not waste your time explaining what is transverse shear locking, but just keep in mind that until a few decades ago, so when actually a few decades ago, almost 40 years ago, there was no proper formulation for this kind of elements. So a finite element of a shear deformable shell was not able to give you a good solution in the thin shell limit. Now, if you are interested in the mathematical reason for this, you can go here, but just to give you an idea of why it was happening, you can look at this image. So as I said before, what is the shear deformation here? The shear deformation is basically this rotation here, okay? So it's taken as the difference between the independent rotation field, which is the entire rotation, minus this rigid rotation, which is the rigid rotation of the normal vector. Now, what is the problem here? It does not come from the theory, it comes from the implementation. So in the theory, you are comparing a rotation with a rigid rotation, which is obtained from the derivative of the deflection, okay? Now, this is fine, but when you go into the finite element discretization, what happens is that this rotation is interpolated linearly. This rigid rotation here instead is computed as the gradient of the deflection, but the deflection is interpolated linearly. So this rigid rotation is actually a derivative of a limit of a linear function, so it has a constant feature, okay? So basically you are computing a shear deformation from a linear function and a constant function, while this deformation should be constant. So when it comes to the finite element formulation, there are cases in which this deformation cannot go to zero. Okay, so there have been many ways to try to avoid it, but the first good attempt was done by Professor Bate. You can find it in the documentation. And he formulated the MITC. So if you are interested, you can go into the documentation and see what it does. But basically, it's a way to reformulate the assumption of the shear deformation through the element in such a way that the element performs well, both in the thick case and in the thin case, okay? So nowadays, if you see formulation like the MITC for the quadrilateral element, or later on, like in 2000, probably, let me see, 2004, actually, this one is much more recent, well, 20 years, but more recent than the other. This formulation has been extended to the triangular element through the MITC3, okay? Same by the same authors. This one was a student of Professor Bate. And if you see that your software has this formulation, you can trust them, you can use them, because they will work both for thick shells and thin shells. If you don't, pay attention to what to choose, okay? So every element which is based on the discrete Kirchhoff theory, which is the discrete counterpart of the Kirchhoff theory, you can only use it if the slab is thin, is really thin, at least 1:10, the ratio between the thickness and the size of the shell, okay? So this one is the main reason why we decided to implement these new elements. The triangular one was completely missing. So before that, in OpenSees, you only had the shell decay GT. So if you wanted to model a thick slab, but you needed a triangular element, you couldn't do that, okay? So you had to use the thin element with all the issues that it has. But there was already another shell element that was based on the MITC4 formulation in OpenSees, which is the shell MITC4. So why did we implement this new element? For a couple of reasons. The plate bending part is only one part of the shell, okay? So it's the out-of-plane behavior. But the shell also has a membrane behavior and other things about how it behaves in large deformation or in nonlinear analysis. But what was important was the in-plane part. In the shell MITC4, the in-plane formulation was the plane formulation of a displacement-based element. So it's a low-order element, and it requires a lot of elements to have a good solution, okay? With this formulation, which is basically the AGQ6, and if you are interested, you can go here. it's similar to the MITC4 in the sense that the strain is not computed only from the displacement. So you have a compatible part for the strain, but you have also an enhancing component of the strain. You can find reference here, but the nice thing about this formulation is that this enhancing strain is insensitive to mesh distortion. Okay, so in the next step, I will talk about this one. What happens instead with the triangular element? The membrane part of the triangular element is probably even more important than the quadrilateral one, because the quadrilateral one, the standard displacement based is not very good, but it's usable. But the triangular element in a standard displacement based formulation is really stiff, so you need a very fine mesh. That's why we decided to use the ANDeS, which once again is similar to the other formulation because it's the assumed natural deviatoric strain. So as all this formulation, they basically take a compatible part and they add another enhancing term to this deformation. Once again, if you're interested, you can go into the reference. Now I will just show you the behavior, how they compare to the others. And a comparison on the in-plane behavior is here. So in-plane bending. So what I'm doing here instead is fixing the plate in the out-of-plane direction and just testing how it behaves in the in-plane direction. Okay, so this is important if you are modeling like deep beams with the shell element on the plane of the beam or shear walls and so on. Here you have only one file. I called it in-plane bending quad, but actually I put everything there, also the triangular ones. So probably I will change the name. But let me close it. And let's open the other one. In-plane bending. Okay, let me explain you what you have here, because you have a huge amount of things. So once again, here I'm comparing everything, and I'm doing, let's look at it. So you have several geometries here. Let's start from the middle. These one are simple beams that are fixed on this side. And here I apply a stress, apply a bending moment actually in such a way that it bends upward, okay? And I want to see how it behaves with different kind of meshes, okay? Like a very coarse mesh, quadrilateral, triangular, a distorted mesh. In this case, the distortion is only, it's like just an aspect ratio distortion. In this case, instead is a real angular distortion, okay? So as you know, all these elements are based on the isoparametric approach. So the key point is that you should try to keep your mesh as regular as possible, okay? So a regular element for a quad is, for example, just a quadrilateral like this with equal sides. For a triangle, it is a perfectly right-handed triangle like this one with same size at 90 degrees in one angle. And then you can have several kinds of distortions. Like distortions like this one are called aspect ratio distortion. So basically, the only distortion is not in the angle. Okay, so for example, if you compute the Jacobian of these elements, you will see that the Jacobian, they actually coincide with the local axis, the x and y local axis. The x and y local, I lost the, okay, here it is. So if you compute the Jacobian of this geometry, this one will be the first column of the Jacobian. This one is the second column of the Jacobian, and they are equal to the ones into the global degrees, into the global coordinate system. They will only change in length. So you have an error, okay, but it's not so drastic. Here it's even worse instead, because when you have an element like this, which is so distorted, you're going to have, for example, the local x-axis, which is like this in the isoparametric space, and the local y-axis in the isoparametric space, which is like this. So they are not 90 degrees. Then through certain transformation in the global space, the y becomes this one, and this one is the error. Okay, so in the isoparametric space, you have a local direction, which is this one, which doesn't match the Cartesian direction. Okay, So these are the two typical kind of distortion that you can have in a mesh. This one is bad, but not so bad. This one is the worst one. So if you can, try to avoid it. But in this case, I'm using all of them to show you a comparison, okay? So in the middle, here you will see the ASDShellQ4, here the ASDShellT3, and then a comparison with the thin shell elements, okay? So the DKGQ and DKGT. And then as a term of comparison, I'm using the shell MITC4 on this side, the MITC4 on this side, because as I told you, in the in-plane behavior, it is based on pure displacement-based formulation. So we will use it as not as a reference solution, but as a basic solution. So you will see what happens with a very coarse mesh, which is regular, what happens with a regular but very fine mesh, and what happens with distorted elements, okay? So here you can see shell MITC4, the two ASD, and the two DKGT or GQ. Then the rest is very simple. So you have a linear time series, nothing special here, an elastic cross-section. Then you have all the formulation, shell MITC4 on the left-hand side, and then we go with Q4, T3, and DKGQ and DKGT. Then the boundary conditions. The first thing we have is, let me go to the geometry, probably it's easier to visualize it. Okay. We have a fixity on the x direction here, and we also have a fixity on the RZ. This is not necessary, but I will talk about it later. Now, for the moment, let's forget about it, and let's look at this one. So I'm fixing the x direction on the entire edge so that I avoid the rigid body rotation. And I'm fixing the Fy, the y degrees of freedom, only at this corner, one of the two, okay, in such a way that, once again, this shell element acts as a beam, so it can shrink to show a zero stress in the out-of-plane direction, okay? And I did it for all of them. And then, since I'm interested only in the in-plane direction, I'm fixing the out-of-plane degrees of freedom. As I said, now I don't want to test the plate bending part. I want to test only the membrane part. And then what I did here, if you look at this one, stress Y at 0, stress Y at minus 10, minus 20, plus 10, it's basically a simple equation. Like if you open this one, I'm applying an axial stress, okay, which is of this form. Compression here, and tension on the bottom, in such a way that it creates a couple like this, okay? Now, of course, to create this equation, I need to create three different equations based on the vertical position of the shell, okay? But this is not important. So what I'm doing with these 4 degrees of freedom, with this 4 boundary condition, is to apply a couple that produces what in theory should produce a unitary stress on top and bottom, positive on top and negative on bottom, +1 and -1. This one would be the reference solution. And we are going to see which one of them is able to give a good response and how this response diverges as you go to the good mesh to the worst mesh, okay? So the only reason why I created 4 of them is because, for example, if you take the one here where the basic, okay, so here the one grid size is 10, here I'm a 0, this one is 5. So if I want a stress that is -1 on top, +1 on bottom, I take Y, I remove -2.5, which is 1/2 of the thickness, and I divide it by 2.5, okay? Of course, if I want to do it on this side, I have to correct this factor. I first have to add +10, so it goes up, and then I apply the stress, okay? It's just an equation. So the key point is that I'm applying a bending moment that produces a 1 -1 stress. And then I have a recorder, boundary condition, a load, and a simple elastic analysis, okay? These are the meshes. As I said, I prepare here, I'm only comparing the distortion, but I'm not using a very fine mesh, just because all these formulations are able to give an exact result, even if the mesh is coarse. But this exact result will get polluted as you deform the mesh, okay? With the shell MITC4, which is pure displacement based, you will never be able to get an exact result with only one element. You need a discretization. Why? Because it has a linear displacement, an almost constant stress state, so it is not able to represent bending properly. Okay, that's why you need a finer mesh. Now, if I'm going to run this one and we will compare the result. Also here it's very fast, so you don't need parallel analysis. Let's open, no, yes, in plane bending, and you will see all of them. Now let's try to see what happens. Let's hide this one. Let's show the surface color map, and now I'm looking at the displacement, okay? Now the displacement, the exact solution for the displacement should be 20, okay? Now, just to show you the exact solution, I will show you this one, okay? Which is the ASDShellQ4. I isolated for a bit. The exact solution should be exactly 20, okay? Given the shape of this one. If you take a beam, you apply a bending moment like that, you will see that this one is the exact solution. And if you look at the stresses in the x direction is exactly +1 at the bottom and -1 at the top, okay? Because it is bending in the upward direction. So even with one single element, you are able to get the exact result, which is the same stress quality that you will have from a quadratic element, but in this case from a linear element. So you have a linear displacement distribution, but also a linear strain distribution. Now let's see how all of them behave instead. Let's start with the standard displacement-based formulation. Now, if you go here, let's go with the perfect mesh, but very coarse, okay? So I isolate this one. You will see that the stress is almost 1/2 of the exact solution. And in terms of displacement, you have 12, once again, almost 1/2 of the expected solution, okay? But this is known, okay? So we know that a linear displacement-based element have an almost constant stress distribution is not able to represent bending properly. So you need a quite good discretization, okay? So in this case, for example, I used 5 elements through the thickness. And here you almost get the exact result, okay? It's not perfect, but it's good. And if I go, so instead of 20 is 90.5. And if I look at the stresses, they are not perfect, but they approach 1, okay? But as you can see, you need a quite fine mesh. So do not underestimate the over-stiffening effect of standard displacement-based element. Okay, so you need a lot of them, because I often see people using just 3 elements on a slab or on a wall. That's never going to work, okay? So you need either you need a special formulation, or if you have a displacement-based formulation, do some tests because it needs a quite fine mesh. Now, what's the problem? This one is fine if the mesh is regular, but now you will see how the solution deteriorates if you add mesh distortion. So let's go back here. This one you have 0.6 instead of 1, but it's not that bad. Now let's see, if you simply increase the aspect ratio of 3, okay, so you have, let's say, the good distortion. The angular distortion is 0, but you have a 1:3 aspect ratio. So instead of a displacement of 20, let's go back to displacement, it's easier to visualize. If I go to displacement, vertical displacement, the solution should be 20. Here I have 12. Let's see what I have here. Here I have 3. It's almost 1/10 of the exact solution. And let's see what happens if you also add in plane distortion, so angular distortion. You have a displacement which is not even 1. So when the expected solution was 20, okay? So when you are using displacement-based element, pay attention to mesh distortions and to the size of the mesh. If you're not sure, do some tests and try to see when you are going to get acceptable results. But in this case, I'm underestimating the displacement of a factor of 20. Is not small. Now, if we look instead at the ASDShellQ4, you will see that basically it gives the exact solution almost everywhere. So if I have a very coarse mesh, which is also regular, I have a perfect solution of 20, and I have a perfect stress distribution of, well, this one is 0 basically. And F1 is exactly equal to +1 at the bottom, -1 at the top, okay? If I add in-plane distortion, only aspect ratio distortion, sorry, the solution is still almost close to the real solution. There is an error of 2 over 1000, okay? So it's very, very small, 0.2% in terms of stresses, and the same thing applies for displacement. Okay, so in displacement, actually, you have 20 because actually the stress converges slower than the displacement, but the error is very small. Now, when you add this one is where you can have problems. Also, in this case, as I said, the formulation that we used for the in-plane behavior is almost insensitive to mesh distortion. It's completely insensitive to aspect ratio distortion and almost completely insensitive to this very strong distortion. As you can see here, the displacement is also almost 20. And if I look at the stresses, they are still very good, okay? So you have 1.1 instead of 1, but basically the error is given by the central element, which is the most distorted. If you get rid of those two, you still have a good solution here, okay? So just put a deformation and you will see what's going on. Okay, so you can see that these three basically deform in the same way. Let's go back to the displacement. So the ASDShellQ4 is almost perfect in plane bending. Now let's see what happens in the ASDShell. Let's only compare the quadrilateral elements now. Let me go on top. I hide the triangular elements and the displacement base because we have seen how the displacement base works. Now let's focus on the enhanced quadrilateral elements. So here you have the ASDShellQ4 and here you have the the DKGQ, okay? The DKGQ has a formulation which is similar, but not exactly the same as the one that we used in ASDShellQ4, which basically still has an enhancement on the in-plane behavior, but this enhancement gets polluted as soon as you introduce in-plane distortion, okay? So if I put the deformation of 0 and if I look only at this one, the solution is exact as the ASDShellQ4. So you have 20. And if I look at the stresses, also here you have 1. So perfect solution also in this case. If I look at this one, so only aspect ratio distortion. Once again, the solution is good. It's perfect in terms of forces and also in terms of displacement, okay? So same as the ASDShellQ4. The only problem is that when you introduce in-plane distortion, it is not insensitive to this, okay? So now you have a displacement which is 1/2 of the expected solution, and the same thing happens. So instead of being 20, is 9, more or less, so slightly less than 1/2. And if you look at the forces, also here, you don't have a force which is equal to 1. Once again, it happens as the more the element is distorted in the angular direction. As you can see here, for example, this element has only one side that is distorted, the other one is right. And the stress solution here is pretty good. But if you go in the middle, it becomes super stiff. So instead of 1, it becomes 0.15, okay? So the idea is try to avoid this one. Then what happens with the triangular elements? So let's go back to the displacement. And let's isolate the ASDShellT3 and the ASDShell and the DKGT, okay? So for the triangular element, you've always read that quadrilateral elements are better, and this is true. We tried to pick the best formulation that we found, which for the in-plane behavior, which is the ANDeS formulation by Professor Felippa. This is the best formulation that you can find for triangular element in the literature, but it's not completely perfect. So basically, you have an exact solution here, which is better than the one that you obtain with the DKGT. The same solution is pretty good also, almost perfect. Let me see, hold on, let me isolate this one. So the perfect mesh is fine. It's actually a little bit softer, but just a little bit here. And if I go to the aspect ratio distortion, so once again, distortion only on the one side to the other, but no angular distortion is still good, okay? Here it is 20, but that's fine. I mean, it seems more correct than the other, but it is not like that. It's that this element is soft, it converges from above, okay? So you have 20 here, but unfortunately, this formulation does not prevent, is not completely insensitive to generic distortion, okay? So here you go to 5, okay? It's still better than the other formulation, because if you compare it with this one, okay, you don't have an exact solution, not even for the regular mesh. So you need to refine the mesh. Here it gets polluted, so it diverges, it goes to 7, and it goes to even less here. Here it is 6, okay? So the point is that in general, you should avoid this kind of distortion. Try to avoid them as much as possible. With the shell element, the ASDShellQ4, you are still able to get a correct solution, but this applies to linear analysis. So if you can, try to avoid this kind of meshes, okay? Because in general, not every element can perform very well. The ASDShellQ4 is only one option, but you cannot find this kind of behavior in every element. So if you can, try to avoid it. The aspect ratio distortion is still acceptable, but also in this case, try to avoid it as much as possible. And this is the last reasons why we decided to introduce the triangular element, is that you can see that the behavior of the triangular element is not as good as the behavior of the quadrilateral element. But in general, there is a rule. It's better a regular triangle than a distorted quadrilateral, okay? So for example, if you have only these two formulations now, okay, let's don't look at the ASD shell now. Let's look at the existing formulation, and you have to choose between a very distorted quadrilateral or a regular triangle. Well, it's better to pick, I didn't show, I want to isolate them. But you can see it from here. It's better to pick a regular triangle, okay? Because I often see people that try to use as much as possible quadrilateral element because they have learned that quadrilateral are better. And in order to use them, when you have a very complex geometry, you end up having very distorted elements. So in that case, it's better if you use a Delaunay mesh and you produce a good quality triangular mesh and a triangular element, because in that case, a regular triangular element is better than a distorted quadrilateral, okay? As I said, only in few cases the ASDShellQ4 can perform good, but as you will see in the next webinar, when you go into the nonlinear behavior, this is not true anymore, okay? So once again, the first rule, try to avoid this mesh distortion as much as possible. That's why we decided to introduce also triangular elements. Okay, so we have another couple of minutes. I just want you to introduce also a little bit of nonlinear kinematics, which is the third reason why we decided to implement these new elements. But then I will talk about the nonlinearity in a next webinar. So the other reason why we decided to implement this element is that all of the shell elements in OpenSees didn't have a proper treatment of large rotations. Handling large rotation is a mess in computational codes. And also in our case, we decided to follow the work done by Professor Felippa. And those of you who are interested, you find it here, which is called element-independent corotational formulation. It's very complex. There is a lot of calculation, but the results are good. Here I provided, actually not here, but in the triangular element, I provided some code in Python for the user to see the behavior of this one compared to other elements, okay? Now I will show them, not in STKO directly, I will show you it in Python, but it's just a numerical test, okay? And I will share also them with you. So if you go here, you will find corotational out of plane, and you will find two files. one for the ASDShellQ4 and the ASDShellT3. Okay, so if you run each one of them, this script will run Python, and in 40 steps, it basically has a cantilever beam, which is fixed on one side, and I apply a bending moment given a certain equation, which you can find it here, but not here. Let me edit it. You can find at a certain point that here I apply a moment, which is given as a function of the Young modulus, the thickness, the size of the element, and the number of revolution that I want to do, okay? So in this case, I want to perform 2 complete rotations, okay? So you put 2 here and you run the analysis. If you want to test it, if it is able to handle very large rotation, you can change this one. Okay, so as you can see here, by here in red, this one is the rotation that I'm applying. So at the time of 1, I'm applying 2 full rotations. So I have 12 point something radians. And this one instead is the vertical displacement of the top point. Okay, so you can see it goes up when it reaches here, then it goes down, then the next time, and it should go down to 0 here. This is the exact solution. Then it goes up of well, less than before, of course, because now it is completely rolled, and then it goes down again at 0. And then I will look at the chart. If you look here, there is also a comparison between the expected exact solution at the end of the analysis in terms of displacement and in terms of rotation, okay? So the exact solution should be 0 in the vertical displacement, and the error is basically 0. And the exact rotation should be 12.6 under a certain moment, and we have exactly the same rotation, okay? So this one is perfect with only 40 time steps. But if you want to test the performance, you can also try to use less time steps, and you will see that it converges pretty fast. For example, if you go here, where it is, here, number of steps, I can also put 10. Let me see if it works with 10. But it should work. Just 10 time steps. Of course, the graph is not perfect, as you can see it here, but the solutions are exact, basically. So because we do all this computation iteratively, it requires a little bit more time, but the solution is perfect, and it converges pretty fast. Okay, as you can see here, just time steps to perform a very large rotation of two complete full rotations. Now, if you try to compare it with the existing elements, you will see one of the problems why we decided to introduce these new elements. So if you go here, you can comment the code of the quadrilateral element, and you can uncomment this one. And I will basically use the DKGQ in the nonlinear kinematic version, okay? So basically in the shell element, you have just one option here. If you use the corotational option, it will activate nonlinear kinematics, otherwise it will be linear. For the DKGQ element, instead, you have 2 different elements. You have the standard shell DKGQ for linear kinematics, or the shell NL DKGQ for nonlinear kinematics. Okay, so I save it and I try to run it with 10 steps. What you will find is 10 steps is that it will not be able to run. So it will have a convergence issue, okay? And it just stopped at 0 because it has a very high residual. When you find these problems, you can try to reduce the time step. And if I remember properly, it doesn't work with 40 as a starting point. Let me try. You will see that it will start to work, but with a large number of rotations. Also, in this case, the residual is still pretty high. Let's try 80. And let's see if it converges with 80 time steps. And then I will show you what is the problem actually. It's not only the convergence one. 80, not even 80, I think. With 100, I should be able to run it because I remember it was running, but with a, let's try 100. Not even 100. Let me try more. More of them. Oh, no, and rolls, sorry. That's why it was not running. I was changing the number of rolls. I have to change the number of time steps. So let's try 40. Okay, it did only one step, but it failed. Let's try 100. Okay, with 100 is running. But you have a certain mistake here. You can see that the error now is 1.46% here and 1.33% in terms of rotation. You are not getting the exact solution, but what is happening is that the displacement does not go exactly to zero, and the more you bend it, the more it doesn't go to zero. So if I zoom here, you will see what is happening. Then I will try to explain you where it comes from. Okay, so if you see here, the element, the more the element rolls, the more it shrinks. As you can see, the element becomes smaller here. And this is basically due to a fact that the update of the system in this element, so the update of the normal vector is not done iteratively. It's done, I think, at every time step, because the solution depends on the size of the time step. So here, for example, with 100 time steps, I can make it converge, but there is an error in the solution. Okay, so here I want it to be at 0. Let's see what happens. And the error is, let's see, let me see the final displacement. The final displacement instead of 0 is 1.4. Okay, 1.5. Let's see what happens if I use 200 time steps. So let's make the time step smaller. And let's see if the solution gets better. It should not, but in this case, if I remember correctly, the solution gets better if you use smaller time steps. You see here, now it is 0.6. When you see behaviors like this, it means that certain calculations are not done during iteration, or probably not correctly. But this is something typical of explicit calculations. Okay, so if you see things like this, try to reduce the time step, or use the other element because it converges better. Okay, so this was, the other reason why we decided to implement this new element. Now we'll go back to the default settings so you can play with it when I will share this file. Oh, of course, there is the same file for the triangular element. Okay, here and also here you can play with it and try to change the ASDShellT3 or the KGT. Let's do a test also for this one. 2 rolls, 40 time steps. Let's try the triangular. Okay, 40 time steps with the ASDShellT3. Also here, an almost 0 error and a very good convergence. Let's try the shell DKGT. Now, in this case, as you can see, you have in each loop a couple of elements, just because you need, of course, 2 triangles to form a quadrilateral, but the concept is the same. Also, in this case, you cannot use the DKGT, but you have to use the NL DKGT. Let's try with 40 time steps. I don't remember if the triangle was working with 40. No, I need to use also here, let's say 100. For the triangle, I don't remember if it was working or not. Let's try. But I think, yeah, 100 is working. So the formulation is basically similar to the other one. No, it stopped at a certain point. Let's try to put more. Let's try to put 200. It gets better, but you have to do a lot of time steps. As you can see also here, you have convergence errors. And well, now I don't want to waste your time. You can play with it, but the concept is that we needed a more robust way of representing large rotation, which is not an easy task. It's true that in this case, we are using an extreme large rotation. Okay, so in general, you will never experience this kind of rotation, but it's a good benchmark to see if your element is working or not. Okay. So I think it's all for these webinars. Now we have room for questions. And as I said, I didn't explain anything about these settings. Let me go back here. So you will see in the new version of STKO that will be released soon that you have few more settings. So the first one is the typical one that you had before. You can choose between linear and co-rotational kinematics, and the same happens here, linear and co-rotational kinematics. But then you have some other option. I will just give you a preview, and then I will dedicate a new webinar for this, which is you can activate the enhancement on the membrane behavior, because sometimes you don't want it, and I will explain you when. Then the drilling degree of freedom. In a new webinar, I will talk about this one. I will talk about the formulation of drilling degrees of freedom, the assumption, and how it can impact nonlinear simulations. So we introduced the nonlinear drilling degrees of freedom, but this one needs another webinar.